hydrogen peroxide is a very pale blue liquid and appears colorless in a dilute solution. It is naturally produced in organisms as a byproduct of oxygen metabolism. It is a strong oxidizing agent. In fact, it is such a highly reactive oxygen species that all living aerobes form peroxide enzymes to decompose the hydrogen peroxide formed within the body into water and oxygen harmlessly and catalytically. Structurally, the hydrogen peroxide molecule is non-planar. It has an open book structure. The presence of lone pairs of electrons on the oxygen atoms and the hydrogen bonding gives the molecule a different structure in gaseous and solid phases. In gaseous state, hydrogen peroxide has a dihedral angle of 111.5 degrees, whereas in solid state, at a temperature of 110 Kelvin, it has a dihedral angle of 90.2 degrees. This affects its physical properties. It has a melting point of 272.4 Kelvin, a boiling point of 432 Kelvin, a vapor pressure of 1.9 millimeters Hg, a solid density of 1.64 gram per cubic centimeter, and a liquid density of 1.44 gram per cubic centimeter. Its viscosity is slightly higher than water at 1.25 centipoise. Its dielectric constant at 298 Kelvin is 70.7 Coulomb square per Newton meter square. And electrical conductivity is 5.1 into 10 raised to minus 8 ohm per centimeter. Chemically, it acts as an oxidizing as well as a reducing agent in both acidic and basic media. So, let's now look at the reactions that take place in acidic media. In an acidic medium, as an oxidizing agent, hydrogen peroxide reacts with ferrous ions to form ferric ions. As a reducing agent, it reacts with sodium hypochlorite and yields water, sodium chloride, salt, and oxygen. This reaction is also used in laboratories to prepare oxygen. Now, let's look at the reactions that take place in basic media. Here, as an oxidizing agent, hydrogen peroxide reacts with ferrous ions to form ferric ions. As a reducing agent, it reacts with iodine to form iodide ions along with water and oxygen. For example, if potassium hydroxide is taken as the base, then potassium iodide salt is formed. On exposure to light, hydrogen peroxide undergoes slow decomposition to form water and oxygen. Metals and traces of alkaline compounds hasten this reaction. And this is why hydrogen peroxide is always stored in plastic bottles and kept in the dark. In recent years, the demand for hydrogen peroxide has increased as it has found widespread use in pollution control treatment of domestic and commercial effluents. In laboratories, hydrogen peroxide is prepared from barium peroxide or acidified sulfate solution. To obtain hydrogen peroxide from barium peroxide, first acidify barium peroxide with sulfuric acid. Barium sulfate is precipitated and an aqueous solution of hydrogen peroxide is produced. The excess water is then removed by evaporating the solution under reduced pressure. This will give us hydrogen peroxide. You can also obtain hydrogen peroxide from 50% sulfuric acid solution. The solution subjected to electrolytic oxidation to yield peroxide disulfuric acid. The peroxide disulfuric acid formed undergoes hydrolysis to form hydrogen peroxide. During electrolysis, hydrogen peroxide is formed at the anode. Peroxide disulfuric acid is formed as a byproduct at the anode. Hydrogen gas is evolved at the cathode. Commercially, hydrogen peroxide is prepared by auto-oxidation of 2-ethyl anthraquinol. First, air is passed through 2-ethyl anthraquinol to yield 2-ethyl anthraquinone and hydrogen peroxide. The product, 2-ethyl anthraquinone, is then reduced. For this, hydrogen under pressure of 1 to 3 atmospheres at 4 degrees centigrade is passed over 2-ethyl anthraquinone. This gives back 2-ethyl anthraquinol, the reactant. This reaction gives a dilute solution of hydrogen peroxide. It is then extracted with water and the solution of the required concentration is prepared. It is customary to indicate the strength of hydrogen peroxide solution in terms of the volume of oxygen at NTP that 1 volume of hydrogen peroxide gives on heating. When the grade of H2O2 in volumes is given, its percentage strength can be calculated. We come across many uses of hydrogen peroxide every day. For example, as a mild disinfectant, as a cleanser, as a bleaching agent in the textile, paper pulp, leather, oils and fats industries, as a pollution control agent in the treatment of domestic and industrial effluents, oxidation of cyanides, restoration of aerobic conditions to sewage wastes, and so on. Thus, we see that hydrogen peroxide is an important compound.